This video is an overview of Mechanics and Materials 1 and an introduction to the mechanical design method. To start this study, we will use the simplest type of loading condition, which is a two-force member which can only carry tension or compression along itself. As the force is applied to the structure, each cross-section in this member responds by stretching and becoming thinner. If we take an element out of that cross-section 1 inch by 1 inch and watch how it responds, as you increase the amount of force on the structure, the molecules get longer and thinner, and as you continue to increase that, the molecular forces cannot respond and they yield and finally fail. In order to characterize this, if you take a 1 inch by 1 inch element of that cross-section, the amount of force that it can support is known as the stress. The amount of force that it is actually carrying at the time is known as the stress. So force per unit area is called stress. The amount, if you take a 1 inch, the original length is 1 inch, and measure how much it is stretched by the applied force, that is called the strain. In order to characterize how this material behaves, we tested by putting a standard sample in a machine that will pull on it and apply a measuring instrument that will measure the amount it stretches as we pull, and develop a curve using more force and looking at the amount the element is stretching, the sample is stretching, and we plot the amount of stress and the amount of strain so that we get a stress-strain curve. And you continue to do that until the material starts to yield. It can no longer, those molecules can no longer support the amount of stress and they start to fail. It gives you an ultimate amount of stress, and finally it breaks. As this happens, we know then, after we've tested the material, we then know how to design using this material and avoid that failure. The loading conditions aren't always that simple. Sometimes you have a structure that has multiple types of loading on it. As an example, if we look at this structure and take a similar element out of cross-section AA, if you do the statics on it, you'll find that that cross-section is not only carrying our axial loading, but also bending and shear. But the axial loading is still analyzed by and compared to our stress-strain curve that we developed for the axial stress. In addition to analyzing a cross-section that is in the material, sometimes the shape is complicated by having the stress concentration of having a discontinuity in the shape, for instance a stepped shaft, or a hole cut for a pin or for some kind of fixture. The way we handle that is that we do the same calculation for our stress, but we use a stress strain, a a stress concentration factor to multiply our stress by to account for the increase in the stress that occurs at the edges of those discontinuities. So still, we are analyzing the axial loading P and dividing it by the amount of area, total area of the cross-section, so that we're looking at a 1 inch by 1 inch element. And even with a complex shape or a complex loading condition, we can still analyze and make sure that it is safe. Another simple type of loading is shear, pure shear. An example of that is a pin that is holding some type of fixture, and as the force is applied, that the cross section of that pin, AA, the molecules tend to slide against each other. The way the molecules respond is by tending to slide, and in order to make sure that we know how that molecule, those molecules respond, we take a 1 inch square, 1 inch square circle, not a 1 inch diameter, but a 1 inch square. It's 1 inch area, 1 inch square, 1 square inch area, and we test it by putting it in a fixture. Here's our round sample, and we put a shear block on it. We have a machine that applies a force to it that tends to shear it, just like this picture shows. And we test it and make sure that when we put a pin in to hold some device in our fixture, that it does not exceed what we got in our testing. Another type of loading is torsion. We use this extensively because the power is transmitted out of a rotating shaft of an internal combustion engine or the rotating shaft of an electric motor, furnishes power to some application. And the way that power is transmitted is by torsion, by torque. And it too applies a stress to the material, and the way the material responds to that is by trying to rotate around its own center with an amount of stress that is greater at the outermost fiber. So as the material tries to rotate around its center, we worry most about the molecules at the outermost fiber because it has the most stress. Again, we'll go into the lab and test this. We have a hand wheel that we put the sample right in here. We have a device that measures the amount the sample twists, and we have a device over here that will allow us to find the amount of torque being applied to it, and we test it and make sure that when we design a shaft or some power transmission, that the material that we've selected will not fail. Another type of loading is bending. Bending tends to cause the material to deflect, and notice that a lot of the structures that we see have bending in some of the members. This case certainly has bending because there's the bending moment. If we analyzed cross-section AA, notice when you pull down on this member tends to bend, and and so if you analyze cross-section AA, it would show up with a bending moment in it as well. The way the molecules respond to that is they tend to be in tension in one part of the cross-section and in compression in the other part of the cross-section. The amount of stress tends to be larger at the outermost fibers. In addition to the bending, the material responds. Notice as this bending moment pushes on those fibers, on that top of that cross section, it tends to push that top slice off, which tends to cause a shear in that material. So that material, those elements inside a bending, has to respond to both the stress trying to pop them apart here and trying to compress them into themselves here, and the stress trying to slide them against each other caused by the transverse shear V. We will not do a test on bending in this lab. You will do a test in Mechanics of Materials 2 on bending. But the material properties we would already know, because it's simply the normal stress properties and the shear stress properties. The method that we will use throughout this course and throughout all of your mechanical design courses consists of two parts. The first part is to find the loading and the stress. In your structure, you need to find the worst case cross section. It usually actually is in bending. It is not usual for notice that is a 2-force member. Usually the worst case of the cross section will be if there's a member in bending, so that you would suspect that might be your worst case. After you've identified the worst case cross section, you do your statics to find all of the loading conditions that exist on that cross section: axial, transverse shear, moment, and torque. And then you find the worst case stresses, if there are more than one stresses, the element that has the worst case stresses. After you've found that number, that numerical value for stress, you go to the next process, and that process says, if this material is loaded like this, I want to make sure it won't fail. So I have to go find the material property values that those molecules can furnish. In addition to that, you never allow the loading conditions to take you all the way up to the yield or the ultimate stress. There will always be a guideline that will tell you how close to that yield you will allow the stress in your member to become. That's called the guideline. Your company will tell you that guideline, or some reference book will tell you that guideline. You apply that guideline and calculate the design stress or the allowable stress. We're going to allow this material, anywhere it appears in our design, to carry that much stress. And then you compare those two numbers. You have a number that came out of the loading conditions. You have a number which came out of how the material behaves in a guideline. You compare those, and the stress caused by the loading condition must always be less than the stress that came out of the guidelines in order to be safe.